very early on, 1997 more or less, we had this very simple probability-based language model where we were computing the probability of a single word, or the probability of seeing bark before dog, or dog barks before, after the. Then around the year, the end of 2000, this whole idea of neural networks kind of exploded. And so people started training neural network-based language models, and these were based on feed-forward network, recurrent networks, or LSTM, so long short-term memory models. And these are acronyms that unfortunately don't mean much to probably to most people, but if you're a bit familiar with the old neural network, NLP, or machine learning scene, it probably means way more. Then at one point there was kind of a drastic curve, and most of NLP abandoned the idea of a language model, which again is just a model which modulates probability, for this idea of distributional semantics and neural embeddings. And the interesting fact is that this whole line of research spawned from the idea of a philosopher, Harris, which suggested that the meaning of a word is basically encoded in its surrounding, meaning that if you see dog and cat appearing in similar contexts, like the dog is chasing the ball, or the cat is chasing the ball, then probably dog and cat hold a similar meaning. And for a few years, this kind of idea dominated the literature and the practice of NLP. Very famous models were born, like Word2Vec, Glove, fast text. Again, people more familiar with this line of research will have like a bit of a nostalgia moment hearing these words. For other, I'm really sorry, it doesn't mean much, but it's not important. It's just to say that at one point there was a huge change of direction, and for a long time, at least in NLP years, we adopted a very different approach to encoding meaning and dealing with text from a computational perspective. And then in very recent years, or 3 decades ago in NLP times, unfortunately, or fortunately, depends how you see it, something started to change. And probably everything started to change when this paper, or better, this model came out. This is Elmo. Yes, if you were wondering, is also a Muppet a character like Bert. In NLP now we are obsessed with the Muppet character. Again, not sure whether it's great or awful. But Elmo is a language model. And Elmo is based, again, on a very large neural network architecture, in this case, a bidirectional LSTM. The main difference, again, with this tradition is the fact that instead of modulating or encoding knowledge or meaning using this philosophical idea of proximity in context, we went back to this idea of encoding probabilities and then let the model do its magic. A second crucial point was more or less at the same time, the same year, when a group of researchers from Google, now I think no one is in Google right now, introduced this work called Attention is All You Need, where they finally, or unfortunately, again, it depends, introduced the idea of a transformer, more or less. So from a purely research perspective, the idea of the transformers was there for like, had been there for like a couple of years, but no one had formalized as well as this paper. And the idea was to just use a mechanism called self-attention, that we will see in a second, that until that point was basically seen just as an extra ingredient in other and larger architecture. So up to that point, we had LSTM with attention, convolutional neural networks with attention. And then the attention is all you need paper arrived and said, well, you know what? Get rid of everything. Just leave attention, and this is the recipe for success. And actually, everything turned out to be true, because in 2018, I think the official date for the peer-reviewed paper is 2019. Again, the Google team released the BERT paper, which introduced, again, the world to this idea of large language models. So models trained to predict or associate probabilities to single words using these gigantic neural networks, in this case, transformers. So I've said transformers so many times. What the hell is a transformers? Well, this is a transformer. We wrote, the slides are still visible, right? All good? Yeah, cool. Ooh, sorry. So again, this is a very chaotic image that, if you're familiar with the machine learning or so on, you can focus a second and draw and take it apart and take some interesting message. But if your interest, as it should be probably right now, is just to get the main idea, the main gist of what is going on, I want you to focus on three main things. The first one is that in here we have two main parts of the model, which are called the encoder and the decoder. The second is this idea that we still have what we called an embedding layer, which is still a piece of the model where we are trying to store representation in the form of numerical value that should hold the meaning of a single word. And then the third very important piece is this idea, this tiny and repetitive subpart of the transformer model, which is called self-attention, which is the magic ingredient of this whole transformer model. Now, before we jump into what is this self-attention mechanism and whatever is actually doing, let's take a second maybe to unpack a bit why this is actually a language models, because you don't see much aside of like random names and so on and so on and so forth. So let's imagine that the input in here is a string of words, like our beloved, the dog is running. As I was saying before, the whole idea of a language model is to assign probabilities to a string of words. So how does a transformer language model, or most of the transformer language models, worked, at least when this was introduced? Well, they worked by using this smart trick, which is called masked language model. So instead of modulating a sequence, so predicting the probability that after seeing the next word is going to be dog and then bark, the idea is to take the dog bark and then hide bits and pieces of this sentence, and then let the model do its magic, let's say, and then output the completed sentences. So if I take the dog barks and then I hide the and barks, I'm just left with blank dog blank. And the whole goal of the transformer is to figure out what the hell is behind those blank. Obviously, being a machine learning model, being a probabilistic model, the actual output is a distribution or a distribution of probability over the whole vocabulary, which basically translates to the fact that the model is just going to pick the single words that are most likely to be filling those blanks. Now, as I was saying, previous language models tend to be more based on this idea of putting one word after the other. And as I think Colin might covered a second, or I'm just gonna say here during my talk, this is actually what is going on with what we call generative pre-trained transformers, like the original GPT and also ChatGPT. If you ever used ChatGPT, you saw that you're basically seeing one word after the other appearing on your screen, and that's actually because that kind of transformers, they still work under the assumption that they need to put one bits after the other. But when they were introduced, transformers and transformer-based language models, they mainly relied on this idea of guessing the missing pieces of different sentences. So just a quick note, and again, this is going to look very technical, but I'm going to unpack it in a second, about this idea of attention being all you need. So what is happening in this attention mechanism or attention layer is actually quite simple from the very high level perspective. What is going on with attention is that we have a layer or a system which takes as input a sequence, which can be either our words or just a set of numerical vectors, and it's going to return basically the same high-level concept. So if we give, obviously, if we give the model a sequence of words, we are going to have our first set of numerical vectors. But if we give 4 numerical vectors as input to the model, we are going to have 4 new numerical vectors. Again, obviously, these numerical vectors are going to be different from the one in the output, are going to be different from the one in the input. How are they going to be different? Well, they are going to be changed by looking to their surrounding words and themselves. So in this case, we have dog in here. And the idea is that the difference between our input vector dog and our output vector dog is going to be a vector which is going to steal, let's say, bits of information from all the surrounding words and from itself. You don't have to worry too much about these weird little other vectors. These are what in transformers are called query, key, and vector, I think. And they're just ways of generating pieces of information that then are going to be merged together. So you can see self-attention as this complicated mechanism that kind of steals information from all over the sentence, or you can see it as a graph, as what we call an attention graph. So again, let's take a longer sentence. In this case, the animal didn't cross the street because it was too tired. And let's imagine that this is our input. Again, our output is going to be the same length. Obviously, these you have to imagine are vectors. And then we can imagine that the new vector for, or the new representation that this machine has for the word it is going to be based on how important other words in the sentence are. So in this case, for the new representation of the word it, animal is the most important, street is also important, and then we have the, it, and the period. Now, you can see the difference between two graphs, which is minimal, as either the fact that a transformer, as you were seeing in the previous image, has a multi-head mechanism, or you can simply see this as the difference between multiple layers of this transformer architecture. And I think this is basically most that I wanted to say about the transformer architecture, because I don't think well, we can have a longer chat later if you have questions. But I think it's going to be more interesting, given the type of meeting that we are having, to talk about Hugging Face, because, as I was saying, this is the new holy grail of NLP. So Hugging Face was born shortly after the introduction of the BERT model. And oops, sorry. Oh yes, thank you for the I'm going to jump actually in Hugging Face later, but yeah, thank you. So Hugging Face was born shortly after the BERT model was introduced, and it was basically a wrapper around the original code and weights of BERT, which basically means that people gathered together and they basically wrote some codes to make sure that using the original source code and the original training model of BERT would be more accessible to other researchers. Oh, why is it? Oh, sorry. Obviously, in almost no time, because we're talking about something that started in 2019, more or less, Hugging Face quickly became the library for language models and transformers, because it was very easy to use. It made sure that experiments were very easy to replicate, and it was also quite easy to expand if you knew the underlying source code, which at the time and kind of still is mainly based on TensorFlow. Nowadays, however, Hugging Face, as I hope I'll be able to show in a second, is the place not just for language models and transformers, but for NLP, computer vision, research, and application. And this is because, as I was saying, Hugging Face is 100% open source. It's almost too easy to use in terms of uploading and downloading models. I personally had some issues with a student of ours that were able to run complicated experiments with transformers, and then they were not able to use a support vector machine, which again is something that doesn't tell much to most people, but to some probably it's kind of a surprise. Not because they were bad students or anything, but simply because we were teaching them, we still are teaching them simple algorithms, but dealing with those simple algorithms is nowadays too complicated compared to how easy it is to interact with Hugging Face. So at the moment, Hugging Face is divided mainly between three. One is the first one is the one containing the models, which are not any longer limited to language model, but we have language models, visual language model, speech to text, text to image, for example, DALL-E. We have speech to speech. You think it, you can find it. And everyone can upload, anyone can upload their models. I have models on Hugging Face. OpenAI has model on Hugging Face. Meta, which is Facebook, has model on Hugging Face. Google has models on Hugging Face. ChatGPT is not on Hugging Face, but because it's not convenient to them, that's how they're going to make money. The second is data sets, which, quite straightforward, is just a collection of data sets. And then the third, which is probably the most interesting one, is this idea of spaces. And spaces are something in between an app, a personal website, a demo, and portfolio. You can use it freely, although you just have access to two CPUs, and you can pay for CPUs. So just to give you some numbers, right now on Hugging Face, there are 141,000. Well, actually, I was checking. This is a photo that I took yesterday, and now it's 143,000 different models. 23,000 data set and more than 10,000 spaces. And this is more or less what you're getting when you're starting to deal with these amazing resources. You enter and you find yourself some models. As you can see, we have OpenAI, which is the company that just released the ChatGPT. We have Stanford, and then we have just single researchers. So, as I was saying, it's probably enough with details and slides. I wanted to show you a bit why Hugging Face is the place to do research, and not just research, but also to start probably if you're interested in NLP, not just from like a theoretical or very high level perspective. Probably going to start with some self PR. So this is, for example, my Hugging Face account. You can see in here this idea of a space. I have some models. I have a data set. This is an organization. And what I really wanted to show you are two things. So the first one is this idea of building yourself a space. So as I was saying, a space is basically like a website. It's a kind of a personal website. This one, for example, is an infrastructure built around a model that I created for my thesis, which is doing something very simple, telling whether a sequence is true or false, but it also has a tiny, small interface, which is basically just telling you whether some words were inside the training and testing data. But let me just jump a second before finishing on why do I keep saying that this is where you want to start if you want to dig a bit into NLP from a theoretical and practical perspective. So let's go, for example, in here. So this, as you can see in here, is again something that I've built in, I think, a little over than an hour. And this is not to brag, it's just actually to say that even someone like me that doesn't have, despite what it might seem, a strong computer science background, because I have a bachelor and a master in cognitive science, and then I jumped into artificial intelligence. This is a space which takes a pre-existing model, which is Whisper, which is a speech-to-text model produced by OpenAI, so the same company that produced ChatGPT, and combines it with a model that I have created for some research that I did, which is classifying dream reports. So what is happening behind this few line of code that I'll jump in a second is that I record something. I think I already recorded something.
The dreamer was walking alone in the forest, followed by a scary monster.
Yeah, so you easily build a button which allows you to record something, and then you submit, and then you wait very little, and there you have your classification. How are these two build this thing, even if you have no idea of how to use a transformer or what is behind the transformer, but you have, for example, some coding knowledge? Well, very easy. Here it's all you need. You need to import some libraries. Sorry, in this case, and this might be interesting for maybe from more a company perspective, you can hide your models. So if you don't want third-party people to or companies to see which model you're using, you can hide the what are you using. But in this case, well, actually, in this case, I'm using some models that used to be hidden because the research that created this model was not public yet. And then I'm using Whisper in here. It's one line, literally one line to call a gigantic speech-to-text model. And then these couple of lines, which, again, they don't have to make a lot of sense to the general public. It's more to show you that we are talking about a resource which is empowering people without a very strong computational background to build something with 26 lines of code, which potentially enables you to use gigantic models or things that were created by third-party apps. Like, for example, combining Whisper with Stable Diffusion. There are a lot of spaces which are completely free where you can touch a button and record the prompt, and then the prompt is automatically transformed into an image by yet another model, which is not yours. It's simply freely available in Hugging Face. And with this, I'm actually done. Thank you very much for your attention. And if you have any question, I'm happy to answer all of them.